Hello, ladies and ladies. Sorry to do this to you during the holidays, but please will you do this and one other little one that I'm going to be passing on to you. This is a section directly on its own, totally isolated from anything else other than one other aspect we've done. So we have differentiability here, and it's tied to continuity. It's just a follow-on from continuity. So I'm going to remind you of continuity just briefly first, and then from there we'll go on to the differentiability. A function f of x is continuous at x of a if the limit of f of x as x tends to a equals f of a. What that really means is there mustn't be any holes in it. There must be any holes where you've got to jump to another place or a point has been replaced somewhere else. So first of all, f of a must be defined. It has to exist. Secondly, f of x, the limit of f of x as x tends to a must exist, meaning in other words that the left limit must equal the right limit. There we are, left limit, right limit. They must be equal to one another. And finally then we get that the limit as x tends to a of f of x is equal to f of a. And there are three requirements. You have done this before. Let's have one example. There we are, we have f of x equaling, and it's a piecewise function, meaning it's split into two functions. We have x squared minus 4 until x is equal to 2, and then we have just x once x is bigger than 2. And we need to show that it's not continuous at x equals 2, which means it must break down on one of these requirements. As soon as it breaks down on that requirement, you don't have to go any further. Well, yes, it's clear from the graph. If you have a look here, we can see this is a discontinuity here, but you can't explain that in words. You actually have to do it formally. You have to use these three conditions and prove. If you're proving not continuous, you have to prove that one of them breaks down. If you're having to prove continuous, you must show that all of them are true. So it needs to be done formally using the conditions. So let's start. F of a must be defined. So we're going to find f of 2. There we are. We know that it's this function when x equals 2, so we substitute 2 into this and we get 0. So f of 2 equals 0. Then we're going to find the limit, the left limit of f of x as x tends to 2, and the right limit of f of x as x tends to 2. So the left limit, as we're coming from the left-hand side, we're going to hit the y value of 0. There it is there. As we're coming from the right-hand side, we're going to hit the y value of 2. There we are. And of course, we need them to be equal. And that's fallen down at that stage because the limit, the right limit is not equal to the left limit. So therefore the limit of f of x as x tends to 2 does not exist, because the left and right limits have to be exactly the same unless there isn't a left or isn't a right limit. And therefore f of x is not continuous at x equals 2. It's broken down. So at this stage now, we're going to go on to differentiability. And it follows the same type of conditions. What it means for a function is it's differentiable if it can be differentiated at every point in its domain. Alright, previously we had it's continuous, so it's continuous, not continuous at x equals 2. But when we get to differentiability, we want to show that it's differentiable everywhere, which means we've got to see if there are any points where it is not differentiable. 3 ways for a function not to be differentiable, and this is informal, this is by looking at it. If a function has any corners or kinks, if you have a look there, it's going upwards and then suddenly it's going downwards again. There's no smooth transition between the two. So exactly at that point, we don't know what the gradient is, which means we don't know what the derivative is. And the same at that point there. We're going to progressively zoom the curve, keep taking smaller sections. And you'll notice as we zoom, the curve gets flatter and flatter, which means that it'll end up pretty close to a straight line, but it always has a gradient of 0, which means it always has a derivative. Now let's zoom the corner. It just continues exactly the same. We can't eliminate that sharp point, that corner. So we have that first condition, not to be differentiable. Next condition, if it has a vertical tangent, and don't worry, you won't be given any of these, it's just later on in life, just in case you need it. You won't need it in order to solve the problems of the world, but you might be asked a question or something when you're doing tertiary maths. And thirdly, if there's a discontinuity. Oops. There we are. Very clearly a jump discontinuity from there to there. Left limit of this function is that y value there. Right limit of this function is that y value there. They're not equal to one another, which means that the limit does not exist, and therefore this function is not continuous at that x value. So a function is not differentiable if it has any discontinuities. Just a little technicality. A function differentiable at A, or a differentiable function, means it's continuous at all points, but the converse isn't necessarily true. There's an example, absolute value of x. It has a sharp corner there. A gradient of -1 until that point, a gradient of 1 after that point, but what's the gradient at 0? There's no continuum through from that to there. So it's not differentiable at x equals 0, but it certainly is continuous. We've been looking at the informal picture. Now we'll start looking at the formal picture where we take the conditions and test them. So as a reminder, there's our definition of continuity. Now what I want you to do as we go through the differentiability is to compare, and you'll see that they're the same rules. The only difference is we have an f prime, f prime, f prime, f prime, f prime, f prime. So it's the same conditions throughout for differentiability, except that it's all about f prime, about the derivative. So the definition of differentiability. What in fact has to happen there, for continuity, the limit of f of x as x tends to a must equal f of a. Here the limit of f prime of x as x tends to a must equal f prime of a. Let's just put that for now. We don't usually have to prove it unless it's discontinuous. If you have to prove that a function is not differentiable and it's due to a discontinuous point, then you prove the point is not continuous, and that makes it not differentiable. F prime of a is defined compared to f of a is defined. The limit of f prime of x as x tends to a exists as compared to just the limit of f of x as x tends to a exists. And then finally that top condition there matching this condition here except with derivatives. There we are. So it's the same system. Boiling down to f of x is continuous at a and f prime of x is continuous at a. So we really have to prove that f prime of x is continuous at every point. And if we're proving it's not differentiable, we just find a point where it's not differentiable. So here we're proving at a point. You could have been asked, determine whether this function is differentiable or not, and you could look straight away and say, aha, there's a corner. No, it's not differentiable there, so we prove it not differentiable there formally, and that means the whole function is not differentiable. So we're going to go through the normal conditions. There we are, differentiability. So we start. We're going to make sure that f prime of a is defined. We're going to show that f prime of 3 is defined. Well, at x equals 3, it's this top function, x squared minus 2x, because that's when x equals 3. So we're going to differentiate it, 2x minus 2, and we're going to substitute 3, and we get 4. So it exists. So f prime of a is defined. Next thing we've got to do is show that the limit of f prime of x as x tends to a exists. So we're going to find the left limit of f prime of x and the right limit of f prime of x. To find the left limit, all we do is say, well, coming from the left, it's on this function. So therefore we're going to differentiate that function and substitute 3. And we get 4. Notice, left limit. Little minus sign in the, what shall we say, the exponent or whatever it is. Superscript. Now, for the right limit, we're going to take f of x equals 3. And we're approaching from the right. It's always the y value. We're not going to be looking at the y value of 3, but it's always this function here. When you differentiate it, we get 0. So the derivative is always 0. So the limit as we approach from the right is 0. Remember, we're doing the limit of the derivative. So there we are. The limit of f of x as x tends to 3 from the positive side, which means it's on that function, which means the derivative is 0. And no matter what you do, the limit is always going to be 0 because it's a constant. Sorry, I had to take a little break to cough my lungs out. So what that means is the left limit is not equal to the right limit. So the limit of f of x as x tends to 3 does not exist, because the f prime of x as x tends to 3 does not exist because the left limit is not equal to the right limit. Which means that f of x is not differentiable at x equals 3, which means, plain and simple, that f of x is not differentiable. Full stop. There are notes on this, just copies of this PowerPoint, and there will be exercises at the end.